Welcome to aminacademy.com. In physics, let us discuss about isobaric process. An isobaric process is a process occurring at constant pressure. We can say it is constant pressure process. The first law of thermodynamic equation for the isobaric process remains the same as the pressure remains constant and because of the volume change. The system does work. Work done can be calculated by the following equation that the PV diagram of the isobaric process is given. Here, this is volume, this pressure. Here, isobaric, that is pressure is constant, so P1 equal to P2, a straight line. Under this straight line, we have to draw a perpendicular line to the volume axis, so it cut V1 and V2. Now, if you calculate this area of this figure, we can say it's a work done by isobaric process. For an isobaric process, we write du equal dq minus dw, and which is equal dq, instead of dw you can write minus p into v2 minus v1, that is pdv, or rearranging the terms dh equal dq. This expression, often used in chemistry and physics, can be regarded as the isobaric form of the first law, dH equal to dQ. That means change in enthalpy is equal to change in, that is heat. Only holds the isobaric process. An example of the isobaric process includes the boiling of water to steam or the freezing of water to ice. That is, suppose if you are keeping a vessel in a open fire it and heat it, what happened that it's which is increased, this heat is increased up to boiling level due to that work done by the gas. That means we are giving heat energy which converted to as work done. In the process, a gas either expands or contracts to maintain constant pressure, and hence the net amount of work is done by the system or on the system. The amount of heat, that is dq, is partly used in increasing the temperature dt and partly used in doing external work. One of the perfect scenario of the isobaric process is the reversible expansion of an ideal gas. Here the dq equal to Cp dt plus Pdv. This is the equation for isobaric process. Work done by a gas in an isobaric process is W equal to integral V initial to V final Pdv. If we integrate this Pdv with respect to the initial conditions volume 1 to volume 2, will get work done by the gas. Look at here, this is area under the line where it is work done by the gas, that is Pdv. Since the pressure is constant in an isobaric process, the integral becomes W equal to Pi, take out as a constant, integral Vi to Vf dV, which is equal Pi Vf minus Vi. Integrating dV gives V final to minus V initial, which is equal Pi pressure initial into change in volume dV. For the gas expands, V final volume is greater than Vi, so dV is greater than positive edge, that is, and the work done by the gas is positive. When the gas is compressed, that is when Vf is lesser than Vi, that the final volume is lesser than initial volume, so that delta V is lesser than 0, and the work that is done by the gas is negative. The work done by the gas is represented on the PV diagram by the rectangular area under the isobaric path. Whether the area is positive or negative depends on whether the gas expands or compresses. When gas is expanded, this positive work done by the gas, and if you compressed, work is done to the gas, that is work is done on the gas to compress the gas. Look at this example. The following graph shows VT graph of isobaric process at two different pressure. Identify which one occurs the higher pressure. Here is a PV diagram. P1 graph is like, P2 is here. From the ideal gas equation, we know that V equal to mu R over P into T. Then in VT graph is a straight line passing through origin. The slope of the line is mu R by P. The slope of VT graph is inversely proportional to the pressure. If the slope is greater, lower the pressure. Here P1 has larger slope. P1 is larger slope than P2. So P1 have, therefore P2 is greater than P1. Suppose the graph is drawn between temperature and volume, temperature along x-axis and volume along the y-axis, then we'll still have P2 is greater than P1, which means here from this, using the slope of these two lines, P1 gives greater pressure than P2. One more example. 1 mole of an ideal gas initially kept in a cylinder at pressure 1 megapascal at temperature 27 degrees Celsius is made to expand until its volume is doubled. How much work is done if the expansion is adiabatic, isobaric and isothermal? Second part, identify the process in which change in internal energy is least and is maximum. Show each process on PV diagram. Name the process in which the heat. Take these constants. Here, in an adiabatic process, the work done by the system is work done equal to du nr over gamma minus 1 into T2 by minus T1. Here, the relation, adiabatic relation P1 V1 for gamma is P2 V2 gamma. We have to use these values gamma, P and V. We can by T1 by T2. By using this relation, we can find the value of T2. Initial temperature is given as 27 plus 273, that is 300 Kelvin. From this relation, we can find T2 and apply this T2 here. We can get work done. For more detail, we'll discuss adiabatic process separately. Next, in an isobaric process, the work done by the system equal to PdV, that is P into V final minus V initial. Here, the given V final is 2 times V initial, that is volume is increased double. So, work done equal to 2 PVI. So, to find VI, we can use the ideal gas law for initial stage P1 PIVI equal to RTI. Therefore, work done during the isobaric process is equal to W equal to 2 into 106 into 24.9 into 10 minus 4, which is equal to 4.9. So, these values are done by using these constants and relations of isobaric process. In isothermal process, the initial room temperature is constant. Then W equal to, here that is, we can use it this one as PV equal nRT. From this relation, we can get, for isothermal process, we can use these values to get, therefore, work done equal to work done equal to P ln V2 by V1. By using this relation, we can get the work done. Comparing all three processes, we see that work done in the isobaric process is greatest and work done in the adiabatic process is least. By using these values, we can compare it. The PV diagram is shown. Isobar, isothermal, isobar, isothermal, adiabatic. Area under the curve AB work done during the isobaric process. This work done under area under this curve AB is work done by isobar. Area under this curve gives work done by isothermal. Area under this curve work done by adiabatic process. In an adiabatic process, no heat enters into the system or leave from the system. In an isobaric process, the work done is more so that heat supplied should be more compared to an isothermal process. This comparison we have done. Please subscribe our YouTube channel.